25 is on increasing and decreasing functions. So it says in pre-calc, you learn how to sketch rough graphs using transformations of parent functions. So in calculus, we're actually going to learn how to sketch everything. We're going to know any graph that we're given, how to sketch it, what it looks like, even if we don't know like the end behavior of a parent function. All right, so in order to do this, the first step we need to learn is what's called the increasing and decreasing test. So it's pretty basic. Basically, if you take the first derivative and your first derivative is positive, then that means f, the original function, is going up. It's increasing. Okay, but if f prime of c is less than 0, right, then that means that your slope is negative, so it means the function is going down, it's decreasing. Okay, it's pretty basic. We've done this on the number line with the arrows going up, down, up. That's what we were doing. Okay, so number 1 says find where the function is increasing and decreasing. So if we find the first derivative, we have 12x cubed minus 12x squared minus 24x. All right, and we can pull out a common factor of 12x. Oops, 12x. So when we do that, we get x squared minus x minus 2, which then factors, because we're trying to find our critical values, just like we talked about last time. So when we have 12x times x minus 2 times x plus 1, we get x values of 0, 2, and negative 1. Okay, those are what we call critical values. So those are the numbers that we put on the number line. Okay, so we draw a number line, and we put them in order, so negative 1, 0, and 2. And we test in each interval. Now what we did in algebra 2 is we did like a little box, and we said, okay, well I want to test like negative 2, I want to test negative 0.5, I want to test 1, and then I want to test 3. So we picked numbers in each interval. Ugh, my alignment's off here, it's driving me crazy. All right, and then we decide if it's positive or negative. So in order to decide if something's positive or negative, we're plugging into the derivative. Okay, let me fix my orientation real quick. All right, so as we test, if I test negative 2, and I'm testing it right here, I get a negative, and then I get a negative, and then I get a negative, right? So negative 24, negative 4, negative 1. So those actually multiply, negative times negative times negative, to be a negative. So we get minus there. So when we test negative 0.5, we get a negative, but then negative 0.5 plus 1 is a positive number, so we get a positive. And when we test 1, we get positive, negative, positive, so we get negative. And when we test 3, we get positive, 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 so we get positive. Okay, it's not always going to alternate like that. Okay, there. All right, so this means that we go down, we go up, we go down, and then we go up. Okay, which makes sense because look at the original. It's an x to the fourth function, right? X to the fourth functions will often look like a W. Okay, and this is what this is looking like. Sometimes they'll look like kind of a more flat, I guess, parabola, so more flat on the bottom. All right, so we want to find where it's increasing and decreasing. So we say it's increasing on the interval negative 1 to 0, and then again on the interval 2 to infinity, and it's decreasing on negative infinity to negative 1, and then again, you can write a union or a comma or whatever. And then again on 0 to 2. I usually put commas between them. All right, that's all it's asking. So that's what I accidentally put on your homework. I think you guys can handle that. All right, so number 2. So now it says draw a graph showing all local extremas, showing all local maxes and local mins. Okay, so this is the first time we've had one where it says, like, actually draw a graph. Okay, we know that it's an x cubed graph, so it should probably go up and then down and then up. So let's go ahead and verify that. So when I take the derivative, I get 6x squared plus 18x minus 24. So I can pull out a common factor of 6. And when I do that, it factors into, what did I do here? Oh, I said 2. You could have got a bonus point. You guys just got to pay attention there, man. So I get x minus 1 and x plus 4. So I get x equals 1 and x equals negative 4. All right, so I end up putting those on the number line. and I test in each location. So we just said what we think it does. We think it probably goes up and then down and then up because it's going to be like an x cubed function, right? Sometimes x cubed functions only have one critical value, right? The normal y equals x cubed only has one critical value. That's when it is increasing then increasing again, right? But this one has two. So since it has two, I'm thinking it does go up and then back down and then back up. Does that make sense? So if you know that on the AP test, you don't have to waste time plugging in. You can do plus, minus, plus easily. But we'll go ahead and test it since we're first learning this. So if I test -5, the 6 is always positive. -5 minus 1 is negative, times -5 plus 4 is negative. Negative times negative is a positive, right? So you should get to the point where you don't need to draw that little box of values. So if I'm testing 0, I get a negative and then a positive. So I get a negative. And if I test 2, I get positive, positive. So positive. So I go up, and then I go down, and then I go up. Okay. Now, in the AP test, I just want to mention you should be very, very specific. Okay, so you cannot mix up definitions. So if I say f prime is positive, I don't want to say that f prime is increasing. Okay, that's not using correct, like they're very, very picky about the wording. Okay, f prime is not increasing. F, the original function, is what's increasing. Does that make sense? So if f prime is positive, f is increasing, right? So be really careful about that. You don't want to say f prime is increasing. Or f is positive, right? That wouldn't work either. All right, so we know that we probably have a local max here, and we have a local min here. How do we know that? Yeah, look at the arrows. It goes up and then down, right? And the slope at the top is 0. And then it goes down and then up, so that's creating a local min. Okay, that ends up being what we call the first derivative test. All right, so now we want to find how high and how low it's going. So I'm going to find f of -4, and I'm going to find f of 1. So f of 1 is going to be 2 plus 9 minus 24 minus 10. Anoop, can you find f of -4 for me? All right. It is 102? I think you're right. All right, so f of -4 is 102. So if you're sketching a rough graph, don't do 102 tick marks going up, right? So just do a little 102. Yeah, approximate. And then -23, not even close to being the correct scale, right? But we'll go with that. And then if you want to find another point, sometimes it's useful to find the y-intercept, because we know we're going up and we're hitting that point, and then we're coming down, but we don't know where we're crossing the y-axis. Can you guys easily find the y-intercept? -10, right? Oops, I didn't draw this very well. So I'm going to go up, I'm going to hit that, I'm going to go through -10, and then I go down to that's my lowest point, and then I go back up, right? So that's a rough sketch. Now, obviously, in calculus, we can find lots of other points. We could find x-intercepts, right? So y equal to 0, try to solve. That one would be pretty tricky to do. But yeah, we're going to have lots of things on our graph eventually. Yes?
Whenever you say that you're like testing the numbers, yeah, like it's positive and what are you testing?
I'm testing in the derivative. I'm testing here. So when I'm testing like -5, for instance, I was saying 6 is always positive. -5 minus 1 is negative. -5 plus 4 is negative. So negative times negative is positive. All right, so the first derivative test. So it's exactly what Jay just said. So it says, suppose that c is a critical number. We have a continuous function. That continuous function thing will be important. I'll talk about that. And it says if f prime changes from positive to negative, so if my f is increasing and then decreasing, then f has a local maximum. If f prime changes from negative to positive, then f has a local minimum. So you can draw like little sketches there if that helps. If f prime does not change, if it goes from positive to positive or negative to negative, right, then that's just one of those places where we have kind of like x cubed, where it tapers off to a slope of 0, but then continues to go up. Or the other way, like this, right? Some textbooks call that a saddle point, which is kind of weird. Saddle points we actually talk about in Calc 3 when we have 3 dimensions of calculus. So it's kind of weird to call this a saddle point. But do you guys see where they're getting the saddle point idea? A saddle point in Calc 3 is like where you have both a maximum and a minimum, and this is kind of like that. It's kind of like a minimum here, right? And it's kind of like a maximum there. So when you sit on the saddle of a horse, you're on the maximum of the horse's back. Does that make sense? The horse's back is rounded, but you're on the minimum of the saddle. I think the saddle goes like this. I don't know, it's kind of weird. Yeah, it's kind of rounded up like that. All right, so number 1, so find the local extrema of g of x equals x plus 2 sine of x. So when I take the derivative, I get 1 plus 2 cosine of x. So setting it equal to 0, I get negative 1 over 2 equals cosine of x. So on our unit circle, that happens in 2 locations. Yep, so it's going to be at not pi over 3, 2 pi over 3, and 4 pi over 3, exactly. So we put those on our number line because those are our critical values. But we also have to put 2 other points on our number line. So we don't have arrows here. Yep, because this is a closed interval. So that is always very important. We talked about that last time. If you have a closed interval, you have to put the endpoints as critical values too. So check endpoints. They will always try to trick you on the test with that, on the AP test. So we put those on the ends of our graph. Okay, so those can be possibilities for maximums and minimums as well. All right, so if I'm, oops, I didn't do negative. No one caught me on that. Negative 2 pi over 3. All right, so you 2 bonus points you could have gotten today, man. Gotta wake up. This is like your Friday, right? It's really Thursday, but you know, school tomorrow. All right. All right, so if I'm testing, let's say I test pi over 2. So if I try pi over 2 in the derivative, so I'm trying it right here. What's cosine of pi over 2?
0.
0. So I have 1 plus 0. 1 plus 0 is positive, right? So I get positive. All right, let's say I try pi for the next one. Pi. Cosine of pi is going to be negative 1. So I have 1 plus 2 times negative 1. So 1 minus 2 is going to be negative. If I try like 3 pi over 2, cosine of 3 pi over 2 is 0. So 1 plus 0 is, again, positive. So that means that our function is increasing, decreasing, increasing. All right, so when we talk about our local maxes and mins, we actually have 2 local mins and we have 2 local maxes. Okay, do you guys see where they're located? So this one's going to be a min, and 4 pi over 3 will be a min, 2 pi over 3 will be a max, and 2 pi will be a max. And this is because the graph ends, right? There are endpoints on the graph. It's a closed interval. So we have to write down all of them. It's fun. So local min of something at x equals 0, and another local min of something at x equals 4 pi over 3. And we'll talk about the local maxes as well. So local max of something at x equals 2 pi over 3, and local max of something at x equals 2 pi. All right, so if I have to find a whole bunch of values like that, a whole bunch of y values, what I will typically do is I'll just put x plus 2 sine of x, the original, in for y1 on my graphing calculator, and I'll just find all of them using the table. So let's go and do that. So get your calculator out and put it in for your y1.
The original equation.
Yep, the original, because you're trying to find the y value that goes with it. So I put in 0, 4 pi over 3, 2 pi over 3, and 2 pi into my table. All right, so when I do that, I get 0 for the first one. So local min of 0 at x equals 0. For the next one, I get a local min of 2.457 at x equals 4 pi over 3. When I plug in 2 pi over 3, I get a local max of 3.826. And then 2 pi, I actually get 2 pi. I get 6.283. So we write 2 pi as well. All right, so those are my answers. If I asked you the absolute max, what would be the highest point? Yep, so you could say local and absolute here. And if asked for the local or the absolute min, 0. Yeah, so that would be absolute and local. Okay. All right, next up. So number 2, so it says find the local extrema of f of x equals x cubed minus 3 over 2x squared. Okay, so go ahead and take the first derivative and find the critical values. So you get 3x squared minus 3x. We pull out the common factor of 3x, so we get x minus 1. We set it equal to 0, so we get x equals 0 and x equals 1 as our critical values. So if I test in the first derivative, so I'm testing in the 3x times x minus 1, and I try like a -1, I get negative times negative is positive. If I try 0.5 or 1/2, I get positive and negative is a negative. If I try 2, I get positive, positive, which makes sense for it to go up, down, and up because the parent function is x cubed, right? It's an x cubed graph. This one doesn't have any endpoints. So these two are going to be, this is going to be a local max, and this one's going to be a local min. So we write that out. So we say a local max of something at x equals 0. Can you guys plug that in? Pretty easy. What happens when you plug in 0 to the original? 0. Yep. And then local min of something at x equals 1. That's an easy one too. Yeah, you get 1 minus 3 over 2, which is -1/2. Okay, so those are our answers. All right, number 3, a little bit harder because we have rational exponents, so fractions of exponents. So I find the first derivative. So I get 5/3 x to the 2/3 minus, when I do 3 times 2 over 3, I get 2, x to the -1/3. So when you have exponents and some of them are positive and some of them are negative, you actually will need to get common denominators. Okay, so we're going to get common denominators. So I'm going to do 5x to the 2/3 all over 3 minus 2 over x to the 1/3. And I want to combine those into 1. Because when I'm finding critical values, I want to find when the numerator equals 0 and the denominator equals 0. Okay, and it's kind of weird here. We need to combine them into 1. So I'm going to multiply by x to the 1/3 and x to the 1/3. And I'm going to multiply by 3 over 3. So x to the 1/3 times 5x to the 2/3 becomes just 5x. And then minus 6 all over 3x to the 1/3. So I want to set this equal to 0, and I want to set this equal to 0. So numerator and denominator equal to 0. Let's look over here. So 5x minus 6 equals 0. Oops. And I have 3x to the 1/3 equals 0. So I get critical values of 6/5 and 0. So putting them on the number line and testing, first of all, 0 was what was making it undefined, right? So there's something special happening there. I always make sure that it's not an asymptote. Because if it's an asymptote, then maybe there's not a max or a min, right? We talked about how f had to be continuous in our definition. Let me go back there. We said that f had to be continuous because sometimes maybe you have an asymptote and your slope is positive and then your slope is negative, but there's no max or min there. Does that make sense? So we always have to look for things like that. So in this case, is it an asymptote? So I look back at the original. Was it an asymptote in the original? No, it wasn't. It wasn't making the original undefined. If I plug in 0 into the original, what do I get? I get 0. There's a point there, right? So maybe write yourself a note. It's not an asymptote. All right. If it was an asymptote, what I would often do is I would draw like a little dotted line there, so I remember that it's an asymptote. So it may not be like, it wouldn't be like a max or a min. All right, so I'm going to test -1. So when I test -1 into the derivative, so right here, I get a negative on top. The cube root of -1 is also negative, so negative over negative is positive. If I try 1 on top, I get a negative on top, a positive on bottom, so I get a negative. And if I try 2, I get positive over positive, which is positive. So we go up, we go down, and then we go up. So if we're talking about the maxima and minima for this, we're going to have a local max at 0 and a local min at 6/5. Okay, so local max of something at x equals 0 and local min of something at x equals 6/5. So when we plugged in 0, we got 0. When we plug in 6/5, it's just gross, right? 6/5 raised to the 5/3 minus 3 times 6/5 to the 2/3. Yuck. I think you get negative 2.033. So negative 2.033 when you do that. Check that. All right, does that make sense? All right, next up. So find all of the relative extrema of the function. So we have f of x equals x squared minus 4 raised to the 2/3. So again, we take the derivative, so we're going to use the chain rule. So I have a 2/3. I have the inside, x squared minus 4, raised to the negative 1/3. And then the derivative of the inside, which is 2x. So if I try to clean this up a little bit, if I have a negative exponent, I'm going to put it on the denominator. So I'm going to have x squared minus 4 under a cube root or raised to the 1/3, it doesn't matter. I have a 3 on the bottom with it. And then I have 2 times 2x, so I have 4x on top. So your critical values are pretty easy to see without writing a lot of work. From the numerator, what's my critical value? Yep. From the denominator, what's going to make the denominator equal to 0? 2 and negative 2, right, exactly. So we put those on a number line. We don't have a closed interval, so we keep it like it is. All right, and then I test in the first derivative. So if I test negative 3, the top is negative. The bottom is a little bit tricky to do. Think about negative 3. You get 9 when you square it, right? So 9 minus 4 is positive. Cube root is still positive. So the bottom's positive. So if I try negative 3, I get a negative over a positive, so I get negative. If I try negative 1, I get a negative over a negative. See how that's a negative on the bottom? Because it's 1 minus 4. So I get positive. If I try 1, I get positive over negative is a negative. And if I try 3, I get positive over positive, which is positive. So my function f goes down, up, down, and up. All right, 2 and negative 2 was where it was undefined. The slope was undefined. But is it okay? Yeah, I didn't have an asymptote there. So I always check that. Okay, so it's just where there's going to be like some kind of corner or cusp. Usually if you have like x to the 2/3, something to the 2/3, it's the cusp thing, right? All right, so it's okay. We still get a minimum there. So we're going to say local min of something at x equals negative 2. A local max of something at x equals 0. And a local min of something at x equals 2. Okay, so we have a min, a max, a min. Okay, the 2 and negative 2 are actually pretty easy. What do you get when you plug those in? 0, so both of these are 0. So you could put those together and you could have said negative 2, comma 2, and you could have like simplified some writing a little bit, right? Up to you. And then the local max, what happens when you plug in 0? Ugh, it's not nice. It's negative 4 to the 2/3. I could have made that nicer by doing like negative 8 or something in this problem. Yeah, so we get I'll use the decimal. We get 2.520. Yeah, or you guys could say, so you're squaring it and get 16 and then the cube root. You could also do that. Same idea. All right, does that make sense? All right, so finish up those last couple in your homework then.